Now that we've learned how we fit a least squares line, a question might be, why would we want to do it? One use of the least squares line is that it allows us to evaluate the relationship between the two numerical variables. Another important use is prediction. In this video, we're going to talk about how we do prediction and what extrapolation means and why we don't like it. Using the linear model to predict the value of the response variable for a given value of the explanatory variable is called prediction. It's as simple as plugging in the value of the x in the linear model and looking to see what the resulting y, the response variable, is. According to the following linear model, the model that we came up with previously, what is the predicted percentage living in poverty in states where the high school graduation rate is 82%? All we need to do to answer this question is to plug in 82% for the explanatory variable and solve for the predicted response variable. So we can write our model and simply plug in 82. Note that we're not plugging in 0.82 here, even though we're seeing 82%, because you can take a look to see what the data look like. The high school graduation rate is a value that's between 0 and 100 as opposed to 0 and 1, as shown by the values on the x-axis of the plot. Doing a little bit of math, the result comes out to be 13.84%. So the way we would interpret this number is that this model predicts that in states where the high school graduation rate is 82%, the predicted percentage living in poverty is on average 13.84%. Prediction is a useful and powerful tool, but we want to be careful. Applying a model estimate to values outside the realm of the original data is called extrapolation. In other words, this is simply plugging in a value of the x into the linear model that was not in the range of the original observed data. In fact, sometimes the intercept might be an extrapolation as well. Here we've stretched out the scatter plot of the data that we've been working with to illustrate this. Plugging in 0 for the x value into the linear model will indeed give us the intercept, but does it seem like a wise thing to do? We have no idea if this line actually extends out into infinity as a straight line, or if it curves down, curves up, or curves down even more. Any of these are possible, and since we don't have data from states with such low high school graduation rates, it's really not wise to believe the value of the intercept as a plausible value of poverty rate if high school graduation rate is 0 for a state. Extrapolation doesn't have to happen in the extremes, though. Take a look at this problem. According to the following linear model, what is the predicted percentage living in poverty in states where the high school graduation rate is 20%? Mathematically speaking, this is a very simple problem. All we have to do is to plug in 20 for the high school graduation rate, and the formula will spit out a predicted value for the poverty for us. But is it wise to do? Before we do, we always want to look back at our data. This could be in a scatter plot format or at least looking at the summary statistics, but something that will tell us whether 20% is within the realm of the data that we observed or not. And in this case, because it is not, we do not want to be doing this prediction because it would yield an unreliable estimate.